Okay, class. So see, now starting with total internal reflection. Basically, what happens first understand through here, then we'll discuss what exactly is its definition. Let's say I have the light ray incident from the denser to the rarer medium. Usually we have the light rays incident from the rarer to the denser medium. Now the light rays incident from the denser to the rarer medium. This is our incident ray. Okay. Let's say here we have the incident ray. So this is the normal. So this will become the angle of incidence. Okay. Similarly, what we will get? We'll get here an angle of refraction. Right? Here the light ray will bend and this will be angle of refraction. This is the incident ray. This is the refracted ray. This is what normally occurs. Now, if I increase the angle of incidence, okay, if I increase this further, let's say I have increased it. I have increased the angle of incidence. So what will happen? The angle of refraction, the angle of refraction on the rarer side, this will increase further. So this will be the angle of refraction. This is our incident ray. This is the refracted. Let's have increased it at such a value this angle of incidence is present, and let's say I've increased it such a value that the angle of refraction is just grazes over the surface like this. Means this is complete angle of refraction that is grazing over the surface, means making an angle of 90 degree, and this is our angle of incidence that is present. Okay, so this is still our incident ray. This is our refracted ray. Okay, all these are normal present. What has happened? I have increased the angle of incidence, and at such a point, the angle of incidence is made that the angle of refraction on the other side is 90 degree. See, what are we doing? I have not drawn all the figures. What will happen here? You keep on increasing the angle of incidence, angle of refraction increases. You increase this, it increases, increases, and the point comes where for which one angle of incidence is in such a manner that angle of refraction is 90 degree. Okay. If I increase further, now see, this is already refracted at, means the angle of refraction is already 90 degree. Okay. Increase it further means angle is greater than angle of incidence. The light ray, because see now already, so this will okay, this will be reflected within the surface because it has already become 90 degree. This is fraction. Now see what all things we have over here. The angle of incidence in the denser medium, for which the angle of fraction in the rarer medium is this 90 degree. This angle of incidence is known as the very important topic, and a lot of questions come from this, and the questions are tough from this portion. I'll just tell you, so practice this topic very well, because see, the topic you will find very easy, and in fact it actually is easy. You don't have very complicated topics from this, but here you will have to pay attention for the numericals part, the applications based questions are. Once you are in a good practice of these kinds of questions, you will understand the whole logic. Like, you first have to find this, then you have to find that, like this. You have to apply Snell's law, angle of incidence, you have to use the critical angles value, TIR, and the answer is actually solved. We'll practice questions though. Okay, so the critical angle is that angle in the denser medium for which angle of refraction in the rarer one is 90 degree. Okay, this is our critical angle. Now, if this angle of incidence is greater than this critical angle, means this has been crossed. For this critical angle, already the angle of refraction was 90 degree. There wasn't scope of increasing the angle further. So if you have increased it further, means if you have increased it more than the critical angle, the ray of light tends to increase its angle of refraction further, which actually results in a reflection. And that's why we say total means complete internal reflection. This was supposed to be a refraction process. But since the critical angle has been crossed, we say the total internal reflection. This is known as total internal reflection. Total internal reflection. This is your incident ray, and here only you have the refracted ray, which actually is no more a process of refraction. Now this is a process of reflection. But two different media are present. Technically, it should have been deviated. The incident ray should have deviated normally, as we have already studied. But what has happened here? The ray of light this comes back to in its same medium. So what happens? The ray of light reflects in the denser medium itself. Okay, now I'll repeat this, what has happened over here. We had our ray going from the denser to the rarer medium. Please pay attention to it. Okay, the light ray is going from the denser to the rarer medium with the usual angle of incidence and the usual angle of refraction. Then we increased our angle of incidence a bit. So angle of refraction also increased. We increased our angle of incidence further, angle of refraction increased. Slowly it increased. And a point came for which, for the angle of incidence, where the angle of refraction in the other medium, that is the rarer medium, was 90 degree. Okay, so this angle of incidence for which the angle of refraction in the rarer medium is 90 degree, we termed this angle as the critical angle. This is critical, means now the light ray is at the critical point where it can't be refracted further. Now, if you exceed this critical angle, what will happen? The ray of light will be totally internally reflected, but this phenomena will not occur if the ray of light is passing from the rarer to the denser. This is a very important property. So for total, see, 2 points you have to know. What is critical angle and what is total internal reflection? Other points you have already studied. Critical angle is what? It's that angle in the denser medium for which angle of refraction is 90 degree or just grazing over the surface for the in the rarer medium. And what's total internal reflection? Two things. One is that light ray should travel from the denser to the rarer medium. If the light travels from rarer to denser, there's no point of it. Refraction, normal refraction will occur. That's the first thing. Second, angle should be more than the critical angle. Otherwise, it will be a simple refraction process. Angle of incidence should be more than the angle of the critical angle. Am I clear till here to all of you? Have you understood this?
Yes, ma'am.
Let's see the statement. Others, what about others? Only Muniba is responding.
Mom,
Have
can you
you got it?
explain the total internal reflection? I didn't understand.
See, total internal reflection is now critical angle has been achieved, means an angle of incidence is there. When you have increased the angle, critical angle, means you have increased the angle of incidence so much that angle of refraction is 90 degree. That condition, this angle is known as the critical angle. Okay. Now, if you, this is a normal case of refraction. Two surfaces are there, one denser medium, one rarer medium. Light rays traveling from the denser to the rarer. Okay, not rarer to denser. Light rays traveling from denser to rarer. So you get a normal pattern of refraction that we have studied. You are increasing angle of incidence, angle of refraction is increasing. You're increasing the angle of incidence further, so angle of refraction increases further. A point will come where this angle R will become 90 degree eventually. That angle of incidence is termed as critical angle. Now see Aisha, if you increase this critical angle also further, this is already the critical point where angle of refraction has reached its maximum value, which is 90 degree. It can't be more than this because normal is already 90 degree and 90 degree cannot be crossed. So what happens if you increase this angle further, angle of incidence you have increased. Now the ray, instead of getting refracted, it gets totally internally reflected within the surface because that angle has been exceeded. It's more than 90. So it is technically a reflection process that has occurred within the same area. Now got it?
Yes, ma'am.
Now see, let's read the statement. The phenomena in which a ray of light traveling at an angle of incidence greater than the critical angle. Okay, this is a condition, that's why this is important. Greater than the critical angle, this is the first condition for TIR to occur. Okay, Second is from denser to rarer medium. This is the second condition. Okay. So the phenomena in which ray of light traveling at an angle of incidence greater than the critical angle from denser to rarer medium is totally reflected back into the denser medium only, which is known as the total internal reflection. TIR term can also be given in the exam. Second, the critical angle, because we have mentioned critical angle and critical angle can separately be used also. Angle of incidence in the denser medium, okay, for which angle of refraction in the rarer medium is 90 degree. This is known as the critical angle of the denser medium, okay, denoted by IC or C. Okay, both the symbols are valid. Sometimes you will see C is written for the critical angle, sometimes you will see this IC is written. So all are valid for it. Whatever is taught to you, you just use that. Okay, this much is clear to all? Definition?
Yes, ma'am.
Okay, let's apply a little bit of Snell's law that we have studied. See, at this point, let's name this point as A. Okay, this is A point. If I apply Snell's law at A point, Snell's law at A. See, here, let's say this, the refraction is N1, or this is air technically. This is air. Let's say this is air. And this is some medium with the refraction N, refractive index N. So refractive index of air into, what did I tell you? Same refractive index, same angle of whatever incidence or refraction, whatever angle is given. Here it's angle of refraction. So N into air is equal to sine into R is equal to, now come to this medium, N into sine IC. Now we know R is equal to 90 degree and we know N air is already equal to 1. So 1 is equal to N into sine IC. Sine IC is equal to 1 by N, where N is the refractive index. Okay, N is the refractive index and IC is the critical angle. Okay, this IC is the critical angle. But if just in case there is some other error medium is used, you use this statement. As I told you, this will always remain your main statement more than any other formula. But sine IC is equal to 1 by N is used in most of the questions. All right, questions now we'll start because more importantly, questions are there. First make the figure, then write the statements. Then it will be a little better for you to understand. Please write it, and if there's any doubt, get it clarified. It's an important topic. Okay, please write it.
Done.
Done?
Miss.
Okay, see, now let's practice numericals based on this. You just have this in the theory part, then you have numericals and applications are also there. I'll try to do the applications if time is there. This says that calculate critical angle for glass air interface. Means glass is there, air is there. Now when the light ray goes from the glass to the air, we have to calculate critical angle. Means this must be angle of refraction. This is the normal. This is angle of refraction. This is angle of incidence, which is the critical angle. So you apply the Snell's law. The refractive index of air will be, refractive index of glass will be. Okay. The refractive index of air into sine r is equal to refractive index of glass into sine IC. This is 1, this is 1 sine 90 degree. This is 1.5. This is sine IC. So basically sine IC is equal to 1 by 1.5. So for the final value of IC, you will write it as sine inverse 1 by 1.5. Okay, so this is a formula based question. Let's see some good questions from your NCRT. Okay, write down this. For the Snell's law is important. This whole topic. Yes, Aisha, refractive index of air is 1 that you have to remember also. Aisha, what about your online classes? Have they started? Are they started in the school?
Yes, ma'am.
Okay, so you must be wanting your timings to be changed, no? Yeah, actually, what about your chemistry classes then? Now your chemistry class time has also changed. Okay, let's see.
Done, ma'am.
All right. Let's see this question. This question, see, the detailings I have not written. Whatever is it, I'll just explain you like this. This is air. And this is gas or any other material. Let's say this has a refractive index n. Now, this is the incident ray, which is incident at an angle of 70 degree at this air and this medium surface. Okay, then what happens? The ray of light gets refracted, but when it strikes its other face, the finally ray which should have uh, come out of it actually grazes over the surface, indicating us the fact that this is where the TIR has occurred in this. Okay, so what we do here, we have to find out this the critical angle in this. Okay, that's the task, to find out what's the critical angle here. Now look, you apply Snell's law. Two things you are able to understand here. Here, angle of refraction is there. This 70 degrees given. 70 degrees is the angle of incidence for which the ray has been refracted. The ray further touches the final surface, and before TIR occurs, that is critical angles case, that occurs. Means this angle is nothing but it's the critical angle. Okay, and this, if you extend, obviously will make 90 degree, but this is our critical angle. Now see, if I talk about this plane surface BC, at BC, look here, what is happening? This is the critical angle, and this is air already, the outer medium is air already. So I can say 1 into sine IC is equal to n into sine R, and we know sine R is equal to 1 because R is equal to 90 degree. So I can say sine IC is equal to 1 by n. Till here, am I clear? Can we say it
Yes.
like this? Okay, 1 into sine R, this is R, which is 90 degree, is equal to n into IC. So sine IC is equal to 1 by n, which we have done above also. Okay, now let's apply the Snell's law at this B surface. At AB means at this surface. This is the normal reaction. This is the angle of incidence. Here the refractive index is there. This is the material. This is the angle of refraction. Yes, now at M. Marwa, can you try and tell me how will we apply the Snell's law? Now, this is a very easy part at this M point. If you have understood, you'll be able to tell. Just try.
Yes, ma'am.
Okay, what's the material outside?
70 degree.
Material, it's air.
Yes.
So what's the refractive index of air? Okay, let me write refractive index of air into. What do we do? Then refractive index into जो beta.
Yes, ma'am.
Refractive index of air I have taken, multiplied to, how to apply the Snell's law? What should I write with this?
Sine 90.
Not 90. Sine
Sine
of the angle which is given in the medium. See which angle is given in air.
70.
7.
70.
So this will be refractive index of air in. Correct. Jesleen, can you complete further the surface? Tell me what should
Ma'am, you're lagging. Can you repeat?
complete this. This. I'm saying complete this. Apply Snell's law. Refractive index of air into sine 70 degree is equal to what?
N into sine
N into sine,
IC.
not IC. At the surface, why don't you all check at the surface? See, this is right, N will be there. Apply, look here, this is the scene. This is the angle of incidence, 70-degree refractive index of air is used. It is getting refracted, angle R is present, N is there. N of air into sine 70 is equal to N into sine R. This is how you have to apply the law. Not 90-degree, why 90? This is not BC, this is AB, this surface we are referring to. We've already applied the Snell's law here. Here we've already applied angle of incidence here was present as the critical angle, refractive index was N. This angle of refraction was 90 and this was air. N in 90, N of air into sine 90 is equal to N into IC. This is how you have to apply Snell's law. Refractive index is medium equal to the other medium's refractive index into sine of the angle that is present in that medium. So, and what's the refractive index of air?
1.
1. So this becomes 1. 70's value is given to us. That is 0.9397 is equal to sine R. So we can say sine is equal to 0.9397 divided by N. This is 1 point. Okay. But this R is not useful for us, sine R. Okay, look at this. In triangle MNP, this triangle M, let's say this point is N, this P. This triangle class. This one. Look at this triangle. Okay, look at this one. So here, if we apply angle sum property, IC plus R plus 90 degree should be equal to, what's the angle sum property?
180.
Very good, Aisha. 180. I can say IC plus R plus 90 degrees equal to 180 degree. So IC plus R is equal to 90 degree. So I can say R is equal to 90 degree minus IC. Now let me put the value here. I can say sine of R. Now I can say sine 90 minus IC is equal to 0.9397 divided by N. Sine 90 minus theta is equal to sine 90 minus theta. Sine 90 degree minus theta. Cos theta class. So this will become cos IC, which is equal to 0.9397 by N. Okay, this is cos IC, but we want sin IC. Sin 90 minus IC wasn't useful for us. We need sin IC. Then only we can do something about this question. We want to find out the critical angle. Sin IC we need to get. I hope you know this identity. Cos square theta plus sin square theta is equal to 1. So from here I can say if I want to get sin square theta, it will be 1 minus cos square theta. What's theta here? It's the critical angle. So can I say sin square IC is equal to 1 minus cos square IC? So can I say sin square IC is equal to 1 minus cos square IC, means squaring this term, 0.9397 by N their whole square. Now see, what was our critical angle initially? Sin IC is equal to 1 by N. So sin square IC will be equal to 1 by N square. Sin IC is equal to 1 by N. So can I say sin square IC is equal to 1 by n square, means squaring both the sides. And if this is there and this is there, means both of them are sine square IC, we can equate them. 1 by n square will be 1 minus 0.9397 whole square by n square. Okay. So if we shift this term on the other side, 1 by n square plus 0.9397 whole square by n square will be equal to 1. Correct? If we shift this term over the side, here it is getting subtracted, so there it will be added. 1 plus, this is around 1 plus this whole 0.90, this we have to check. This will be around, let me tell you the answer, 0.9397, around 0.88 it is. So 1 plus 0.88 it is around. So 0.88 divided by n square is equal to 1. That is 1.88 by n square is equal to 1. So n square is equal to 1.88. N is approximately equal to 1.41. That is nothing but root 2. Now question wasn't to calculate n. The question was to calculate critical angle. So what is critical angle? Sine IC is equal to 1 by n. So I can say sine IC is equal to 1 by root 2. IC will be equal to 45 degrees. Getting my point, class? Is this question clear to all?
Yes, ma'am.
So see, these kinds of questions come from your critical angle part, total internal reflection part, Snell's law. Like the concept is very easy, class. What is Snell's law? N1 into sin I is equal to N2 into sin R. Or you can simply say sin I by sin R is equal to N2. And this is the Snell's law, but applications. So these kinds of questions are there. All right, so write it down, copy it. At any step, if you have any trouble, please let me know. The question was to calculate the critical angle. Start writing, class. Yes, Aisha, you can use sin I by sin r is equal to n1 by n2. It's provided you know n1 and n2 are correct. Like sometimes it becomes confusing which is n1, which is n2. That's why I prefer to write it in this manner, because then the corresponding one comes. But if you're sure and which is n1, n2, you can definitely use the actual formula is this only, which you are saying, which you are saying. Okay.
Done. 10.
Okay, your extra classes are just for 1.5 week. Okay, for bio
Yeah,
and
ma'am.
okay. All right. Then all right, Aisha, can you just tell me the timings of your extra classes? Just type the timings. If you have any schedule or something, just let me know that. Done? Besides, see, this is a question from applications only. Optical fibers are one of the applications of total internal reflection. This figure shows a cross section of a light pipe made of glass fiber of refractive index 1.68. Okay, the outer covering is made of the material whose refractive index is 1.44. It says what is the range of angle of incidence. Okay, angle of incident rays means angle of incidence for which TIR can occur. See, if the light ray is entering from here, you have to find out this angle. What is this angle? What is the range of this angle? So that when it strikes here, TIR occurs. This is the question. Getting my point? So refractive indices are given. First, we'll calculate the refractive index. What is 1 by R? Because we know, see, if here TIR has occurred. So for TIR, we know one thing. Look here. I dash, let's say this angle is some I dash. Whatever is this, let's say it is some I dash, we'll be replacing it. It must be greater than critical angle, then only TIR has occurred for TIR to take place. If I put sine, this will be sine I prime is greater than sine IC, right? Sine I dash is greater than sine IC. Okay. This I dash is not required, but see class, I know this angle of refraction. Just understand the technique to solve this question. If I know this angle of refraction, I know the refractive index of this material already, it's mentioned. This is air, I know the refractive index only. If somehow I know this angle of refraction and I apply Snell's law here, I'll get this angle, sine I I'll get. But the problem with this question is that I don't know this angle of refraction. R is missing. Okay, in the angle of refraction, the R is missing. So for this R, if I get this, then using angle sum property, I will get R. If I get this critical angle, whatever is this I dash, because it is not critical angle, it is greater than critical angle as TIR has occurred. If this was critical angle, this would have been like this. Okay, so if I get this angle I dash, this will be 90 minus I dash, that will be R. So that's why we are focusing, we have started from this, we want R so that we can apply Snell's law and get the value of this I. That's the whole plan of this question, okay? So here this is sine I dash is greater than sine IC. Now let's find out what is the sine IC. Okay, sine IC, you know, this is 1 by n. Now what is 1 by n over here? The rarer medium is 1.44, denser is 1.68. The rarer by denser is 1 by NDR, that is 1.44 by 1.6, which is 0.86. Means this 1 by n is equal to 0.86. So I can say sine IC is equal to 0.86. Okay, so that clears the fact that this I dash, sine I dash is greater than the 0.8, greater or equal to, maximum or equal to. That's how we'll obtain the range. Now look here class, if I now use this angle sum property in this smaller triangle, this is angle of refraction. Okay, look at this triangle. The triangle that has been formed now is like this. This is that I dash, which is greater than the critical angle. This is 90 degree and this is the angle of refraction which we want so that we can solve the question further. So we can say I dash plus R is 90. I dash plus R is equal to 90 degree. From here we'll get I dash as 90 degree minus R. Also we know sine I dash is greater than 0.86 from here. Is this clear why this is greater than 0.86? Because sine IC is 1 by n and 1 by n can be calculated using the relative refractive indices concept. Two refractive indices are already given to us. So sine I dash is greater than 0.86. Is this part clear?
Yes, ma'am.
Yes,
Okay,
ma'am.
I'll repeat it though. If there's any trouble, you can let me know. Now I can put this instead of, because I dash is not helpful. Somehow I want R. Now with the help of this, I can introduce R and somehow R is reached, we'll be able to get I. So this will be sine 90 minus R is greater than or equal to 0.86. Sine 90 minus theta is cos R greater than 0.86. Now, as soon as you have cos R, we need the value of sin R, right? Okay, even if you have cos R with this, how will you get? See, sine 90 minus theta you already have, okay? That is cos R. So, we can say sine square R plus cos square R is equal to 1. Why? See, from here you can't get sin R. But if you convert it into cos R and then use this, then you can get sin R like the previous question what we've done. That's what I was saying initially also. Questions are tough, but they have a similar pattern. See, I've been using the same thing in this question as well. So this will be cos R is greater than 0.86. Okay. So we can say cos square r is greater than equal to 0.86 whole square. So sine square r will be 1 minus cos square r. So what is sine square r? See, we are reaching close towards sine square r. Will be greater than or equal to 1 minus 0.86 square. So sine r will be greater than or equal to under root of 1 minus 0.86 square. Is this clear? This much? Let me see
Yes,
what's the
ma'am.
0.86 square. No, it's around 0.739. That is almost 0.74. So that will be 0.26. Value of sine r will come out to be 0.26. This will be the value of sine r. Now let's apply Snell's law at incident. Sorry. I'll increase the steps also. Wait. Sine r is greater than or equal to under root 1 minus 0.74. Okay. So that's why this sine r is greater than or equal to 0.26. Sine r is there. Now let's apply the Snell's law here. What we actually required the angle of incidence. I'm drawing it here. See, this is the pipe. This is air. Angle of incidence, which we have to calculate. Angle of refraction, where we know sine r's value. So refractive index of air into the sine of I, same refractive index, same angle, is equal to refractive index of this pipe, that's the pipe that is coming here, inner part, this part you will take, into sine r. So air is 1, sine I we have to find out. The refractive index of the pipe is 1.68, this region, right? This is 1.68 into 1.68 into sine r is greater than or equal to 0.26. So in fact, this will also be, if I take this, I shouldn't just put the equal to sign because this is greater than or equal to. So this will also be greater than or equal to. So this will be 68. Okay, here the answer is already written above this one. So yes, sine I will be greater than or equal to 0.4368. So I will be equal to or greater. See this, that's why the question said range. Because you are getting more than or equal to. The question didn't say get the exact value. Sine inverse 0.4368. This is the answer. Okay. From here, I am erasing this. I am repeating. Please pay attention. In this question, angle of incidence was asked. That's it. So see, if we got refraction, angle of refraction, we could easily get sine I. Using Snell's law, we can get, if we know, because all the refractive indices are also known and only R is missing. For R, we can use angle sum property, but for that we require this I dash. Now here, since TIR is occurring, we can use that knowledge to find out I dash. So what did we do? We used the concept of TIR, that is sine IC is 1 by n, and the refractive index were present. So sine I dash was caught. Tell me the sine I dash part, have you understood why it is greater than or equal to 0.86? Clear to all?
Yes, ma'am.
Clear or not?
Yes.
Respond. If you have any trouble with any part, please let me know. Now, since we got I dash as discussed, we used the angle sum property to get sine R. How did we get sine R? We had sine IC. We use this angle sum property to write r. Then sine 90 minus theta was cos r. And we can convert cos into sine using this identity. So sine r was given. Then we applied this Snell's law at this angle of incidence. We got I. Fine, am I clear with this question, class?
Yes, ma'am.
Okay, then please write it. 7 to 8:30 on Monday and Wednesday. This is which time, Aisha? KSA time, UAE. Which time is this? 7 to 8:30? This is IST. So 8:30 your class started. Okay, sorry, GST you've written, Gulf Standard Time. So that is how much? 2.5 hours difference is there, no, from India? Or 1.5? 2.5.
2.5.
So 11 o'clock. That will be 11 o'clock. Your class will be till 11 o'clock. IST. Okay. And see, we can't have the class at 11 o'clock, no, Aisha? 11 to 12:30. It's already till 11:30. Like right now, it's 11:16 here in Delhi. It's 11:16. If we start the class at 11 o'clock, it will be very difficult. You tell me, Aisha, how do you want to go about? Like you can be put in that batch, Tuesday, Thursday's batch. That is fine, but Tuesday, Thursday's batch, you have your chemistry class because I think Marwa's your school time changed.
My school timings have been again changed. So can I just request the team to like get back to my previous schedule?
Okay, your timings are changed, Marwa?
Yes, ma'am.
Okay, then that's fine. You both can come in your regular batch in which you were coming the previous one, Tuesday, Thursday, right?
Okay, ma'am.
I'll just inform. Okay, then that will be better. You write it, please. Yeah, because of the chemistry class changing, this was done. Wait, you write it all of you. I'll just inform Marwa and Aisha.
Done, ma'am. Done, ma'am. Done. Done.
Okay, class. So you can leave. We'll continue in the next class. Okay. Thank you then.